Here's the so-called power rule for differentiating x to the n. Nevertheless, here we go. When n equals 1, the derivative of just x to the first power, which is just x, is equal to 1. This should make sense, because what's the derivative measuring? The derivative is measuring output change compared to input change, and in this case, the function is just the function that sends x to x. The input and the output are exactly the same. So the input and the output change is exactly the same. Their ratio is just 1. And consequently, the derivative of x, the derivative of the identity function, is 1. For the time being, we're just going to think about this when n is a positive whole number, but even there, it's pretty tricky. Now, admittedly, when n equals 1, you're probably going to be pretty unimpressed. The derivative of x to the n is n times x to the n minus 1. What's n? N can be any real number except for 0. You should think about why you don't want to plug in 0 for n. When n equals 2, that means we're differentiating x squared, which we studied a little bit ago. Now, here's the power rule. If I plug in 2 for n, I've got the derivative of x squared is 2 times x to the 2 minus 1. Or, a bit more nicely written, the derivative of x squared is 2x. And you'll remember, we really did study this in quite some detail, algebraically, numerically, geometrically. When n equals 3, we can still study the derivative of x cubed in a geometric way. So here's the power rule. You plug in n equals 3, and you get the derivative of x cubed is 3 times x to the 3 minus 1, 3 times x squared. We can see this geometrically. We start with a cube of side length x, and we're going to glue on 3 green slabs of side length x, x, h. Now, in order to actually thicken up the cube, we've got to glue on a few more pieces, these blue pieces and this red corner piece. But once we've done that, now we've built a cube of side length x plus h. How has the volume changed? Well, most of the change in volume happened in these 3 green slabs, and those 3 green slabs have volume 3x squared h. The change in the side length of the cube is h. Geometric argument is showing us that the derivative of x cubed is 3 times x squared. When n equals 4, we're trying to differentiate x to the 4th power. But that would involve not a cube, but a hypercube. It seems a bit ridiculous to try to gain intuition about the derivative of x cubed by doing something as esoteric as studying 4-dimensional geometry. So instead, let's differentiate x cubed directly by going back to the definition of derivative. So let's proceed directly. I want to compute the limit as h approaches 0 of x plus h to the 4th minus x to the 4th over h. What is this computing? This is the limit of the difference quotient. This is the derivative of x to the 4th at the point x. Now to proceed, I'm first going to make this a little bit smaller, since it's a bit too big to work with. This is the limit I'm trying to calculate. The first step is to expand out x plus h to the 4th. And if I expand x plus h to the 4th, this is what I get. H to the 4th plus 4h cubed x plus 6h squared x squared plus 4hx cubed plus x to the 4th. And now you'll notice something very exciting. I've got an x to the 4th minus an x to the 4th. So I can cancel those two terms, and I'll be left with the limit of everything else. H to the 4th plus 4h cubed x plus 6h squared x squared plus 4hx cubed, still all over h. But more good news. Every single term up in the numerator here has an h in it. So I can cancel those h's without affecting the limit. And this limit is the same as the limit of h cubed plus 4h squared x plus 6hx squared plus 4x cubed. Why? Well, look, h to the 4th over h gives me the h cubed. 4h cubed x over h gives me the 4h squared x, and so forth. Now we're practically there. I want to evaluate this limit. Most of these terms here have got an h in it, so when I take the limit, these terms are all 0. The only term that survives is this one, which as far as h is concerned is a constant. It's the limit of 4x cubed as h approaches 0. That's just 4x cubed. And because this whole mess is calculating the derivative of x to the 4th, what I've really done here is shown from the definition of derivative that the derivative of x to the fourth is 4x cubed. This limit calculation is perhaps complicated enough to give us a glimpse into the whole story. What's the derivative of x to the n? Trying to show the derivative of x to the n is n x to the n minus 1. And to do that, we go back to the definition of derivative and try to calculate this limit. The limit is h goes to 0 of x plus h to the n minus x to the n over h. Just like the case when n was 4, the first step is to expand this out. But here it's a bit trickier. Right? To expand out x plus h to the n, I don't know exactly what n is. N's just some positive whole number, so I can't write down exactly what it is, but I can write down enough of it to get a sense of what's going on in this story. H to the n plus n h to the n minus 1 times x plus, and hidden in these dot 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 is all kinds of other terms that have h's in them, plus n h x to the n minus 1 plus x to the n minus x to the n all over h. Just like before, I've got an x to the n and a minus x to the n. So I can cancel those, and now I'm left with just these terms, still a bunch of terms with h's in them. And note that every single term in the numerator here has an h. So I can then do the division just like before. The h to the n over h becomes h to the n minus 1. N h to the n minus 1 times x becomes n h to the n minus 2 times x. Everything in the dot 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 here has at least an h squared in it. So when I divide it by h, everything that's left over still has at least one h in it. This last term, nh times x to the n minus 1 over h, becomes nx to the n minus 1 after I divide by h. And now look, this is a limit as h approaches 0. This term dies, all of these terms with h's in them dies. The only thing that's left is this term here, n times x to the n minus 1. And that means that this entire limit is equal to nx to the n minus 1. This limit is calculating the derivative of x to the n. So what we've really managed to do is show that the derivative of x to the n is nx to the n minus 1.